gains and convex for losses, with losses being steeper, generally twice as steep as gains. So it's a nice theory because it is empirically founded, yet simple and elegant. So let me recap what this part of the lecture was about. Yesterday we talked about framing effects. The fact that if you sum the gains and the losses, you integrate outcomes. If you do the opposite, if you separate them out, you segregate outcomes, then you cancel them if one of them is very small. Silver lining is focusing on the positive one. And then the sure thing principle, the fact that outcomes that are sure across different bets should not matter, yet they do. We have seen the violation of the sure thing principle both in the Alle problem and in the Ellsberg paradox. And then we also talked about certainty effect, ambiguity aversion, which is captured by the Ellsberg paradox, our dislike for ambiguous distributions, and then to reconcile the theory in such a way that we can make predictions and also rationalize behavior, we introduce the concept of probability weighting function, which is central to prospect theory. Unless there are questions or comments, I will continue with the material. Okay, so let's now shift gears and talk about strategic interactions. Many of our decisions in day-to-day life involve some level of strategic interaction. We are generally faced with choices that affect ourselves but also affect the others. We need to coordinate on behaviors, and that gives rise to strategic interaction. So far we have been mostly talking about lotteries and bets, and these are non-strategic, right? It's you against the coin or choosing a lottery. So those are important to highlight behavior, but since we are social animals and since we live in societies and interact with people, known and unknown, we need to also look at strategic interaction, which is going to be very important in order to talk about game theory, which is the study of strategic interaction. So let's talk about some basic definitions in game theory, which is, as I said, the analysis of strategic interactions. A game is a decision problem in which the final outcome depends upon the decision of all players, as well as on the state of the world. A strategy is a complete plan of action that describes what a player will do under all possible circumstances. Right? So if it's two-player, two strategies, you need to not only choose your best course of action between going, say, up or down or left or right, but you need also to do that contingent on the choices of the other players. And of course, the more the players, the more the strategies, the more complex and demanding it is in terms of our ability to contemplate all these scenarios, and so rationality becomes increasingly taxing a requirement. The payoff matrix that we will shortly look at represents the payoffs associated with each possible combination of strategies. And let me now talk about the concept of Nash equilibrium. Is a strategy profile such that each player is playing their best strategy given the decision of the other players. Right? So again, in the simple case, relatively simple case of two players and two strategies, player one will need to put herself in the shoes of player two and evaluate, given that player two chooses one action versus the other, what the possible best outcome is. But both players will be doing this reasoning, and if both do this reasoning, we will end up in the Nash equilibrium where each best responds to the other. Again, this is based on the notion of rationality, which we have seen is not always a good description of reality. Nash's theory states that every finite game, that is, every game in which all players have a finite number of pure strategies, by pure strategy I mean the strategies that I do with 100% probability, because there's also mixed strategies where I randomize between two or more strategies, but to simplify, let's consider only pure strategies for the moment. I was saying every game in which all players have a finite number of pure strategies has a Nash equilibrium. So this is what the theorem by John Nash states. So provided that you have a finite number of strategies, you will find an equilibrium. Have you seen these matrices before, just so I can adjust? Raise your hand if you do, if you have. Okay, so most people, but not everyone, has. So, you know, you can also play around with this at home, but the idea here, should be seeing my cursor, is that this person is player 1, and she can choose between up or down in this simple game. There's only one other player in this game, it's player 2, that instead is tasked to choose between left and right. So let's just do it for the first payoff matrix, and then you can do it for the other two at home. In order to compute the Nash equilibrium, let's say that you are player 1, so your choice is simply up or down. You need to look at the payoffs for you and for the other. So here the first number is the payoff to player 1, the second number is the payoff to player 2. So if player 1 chooses up, depending on what player 2 does, the payoff to player 1 will either be 2, I don't know when, either 2 or 0, right? So in this case, you can, for instance, underline the first 2 to remind yourself that this is your best response, given that player 2 goes left, right? So if in this situation you prefer, you know that by going up, you need also to think, as I said, about what player 2 will be doing, right? So let's look at, because so far I've been talking about the preferred payoff for player 1, but let's look at what player 2 can do, given that I, player 1, go up. Player 2, again, will get either 2 or 0, right? So you know that player 2, if I, player 1, go up, player 2 will go left. So that is the reasoning you do. You do the same reasoning, you know, by contemplating what happens if I choose to go down. And you know that player 2 will go right, because 1 is strictly greater than 0. Here the payoffs are put in such a way that there's no indifference, right? That's when mixed equilibria arise, because in this case, well, simple, 1 is certainly better than 0 from the perspective of player 2. But in certain games, it may be that you're indifferent, and that may give rise to mixed equilibria. You can then do the same exercise from the point of view of player 2, right? And then you will find the solution that is, if there is one, because it's not always the case that there is a best response, but if there is a dominant strategy, then you isolate your Nash equilibrium. Of course, this is a particularly reduced complexity case. You can already grasp here that even with only 2 players, but one more strategy, you have to do more reasoning about the possible outcomes. And with n players and n strategies, it becomes much more complex. So let's look at some common types of games. One that is quite interesting is the pure coordination game. In these games, the interest of both players, unlike in the prisoner's dilemma, where they are contrary, the interest of player 1 conflicts with the interest of player 2. Here, both players want the same thing. So you can think about many real-life examples, such as driving on the left versus driving on the right. if we are in a country where everyone else is driving on the right, like in Italy, you definitely want to do the same, right? So it's a coordination game situation. You're better off when everyone sticks to the same rule. You can have other classes of games, such as Battle of the Sexes, which is an impure coordination game where each player desires a different cooperative outcome. So, for instance, it's called Battle of the Sexes because the way it was framed initially, which is a bit dated nowadays, was that it's a couple deciding, what to do for the evening, and he wants to go to see the football game, and she wants to go to the theater. Both of them prefer to do the same thing, so it's also a coordination game, because both are given the choice, given that the other person does one thing, they also would like to be with her. They don't want to be alone. But there's a tension, because so in this case both are equilibrium, the equilibrium where both go to the stadium and the equilibrium where both go to the theater. But of course they are not equal, like driving on the right hand side of the street, which is to the same benefit to everyone. In this case, the man would strictly prefer to go together to the stadium, and the woman would prefer theater. So that's the Battle of the Sexes. One quite general and important class of game that includes many games such as the Prisoner's Dilemma is the zero-sum game, which in a way means that whatever one gains, the other loses, right? So here we are basically splitting a pie. So if I take a bigger slice, the remainder for you will be smaller. So these are situations in which, of course, there's a big tension between self-interest and collective good. So why was it called Prisoner's Dilemma? The metaphor, which applies to many other problems, including environmental degradation and climate change, is that of two people being caught for robbing a bank, for instance. And so they are separately and without communication, this is important, they are questioned by the police, they are interrogated in separate rooms, they cannot communicate, and the incentives are such that if the two thieves cooperate among themselves, they would get away with only 2 years. So they would, in this scenario, they would both say, I'm innocent, and the other person is innocent. So the police in this situation does not have hard evidence that they did the robbery. So minimal loss in a way, but they still have to do 2 years in jail. Now, the really bad situation is depending on whether you look at the collective good or the individual good, but let's look at the opposite scenario. So this is cooperate, 2 years for both. If both defect, meaning they say, I'm innocent, the other person did the robbery, then the police knows that both did the robbery, because both accuse the other. So they both stay in jail for 10 years, but maybe there is some uncertainty about whether really both did it, so that's why it's not 20. Now, from the point of view of a cooperator, the worst possible outcome, so you're player one, you choose cooperate, and the other cooperate, great. But if you choose cooperate and the other one says that he's innocent and you are the one who did it, then you get the maximum sentence of 20 years, which of course individually is not a best response, right? So because of this, both players reason, well, too risky, I will defect. But if both players defect, you end up in the only equilibrium, which is a not very good one, right? Defect, 10 years, when both could have gotten away with 2 years. So these two, CD and DC, actually never materialize, but the temptation to defect, right? Because put yourself again in the position of player one. You say, well, you know, if I cooperate and the other person defects, sorry, you're contemplating as player one whether to cooperate or defect. But you see, you need to look at your payoff, and cooperation is always dominated, right? Because here a lower number is better. So you say, well, 2 years is not so bad, but I could do even better and get out of jail right away. And then both of them think this way, both of them defect, and both of them end up in jail for 10 years. So this is why it's called prisoner's dilemma, and it is very much interesting from public policy and environmental economics, because it captures in a very simplified manner the tension between, you know, for instance, the individual self-interest to avoid actions that are somewhat costly, either in monetary terms, like buying sustainable goods or switching to an electric car, or in convenience terms, you know, we still find it cheap and convenient to fly instead of taking the train. But of course, if the collective group does all do that, you know, we end up over exploiting the commons and degrading the environment much above what would be sustainable. So let's talk about a few more important concepts in game theory. An outcome X is said to Pareto dominate another outcome Y if all players weakly prefer X to Y, and at least one player strictly prefers X to Y, right? So this definition comes from Wilfred Pareto, an economist, and the idea is that in this situation, it is the dominant strategy because all players are either indifferent, that's a weak preference, and at least one is strictly better in this situation than if he or she chose the alternative Y. So that's from the point of view of one player. If we look at the group point of view, an outcome is said to be Pareto optimal if it is not Pareto dominated by any other outcome, right? So that's the socially optimal decision that does not hurt anyone. Any questions or comments? All right. So, a couple more concepts. Cheap talk refers to non-binding verbal agreements. So these are important because the theory predicts that in games, cheap talks should be disregarded. You know, imagine that the two robbers have a way to send a signal or somehow talk to each other before they are questioned by the police. You know, according to theory, this should not make a difference because you will say, yes, I will cooperate, okay, I will not say that it was you, both of them say it, but then they are still tempted by defection due to the incentive structure. So in principle, it should not make a difference. In reality, as we will see in the later lectures, when we play experiments and also we look at the results of experiments that have been performed before, we will see that these verbal agreements, even if they're non-binding, so cheap talk from an economic perspective, are quite important, especially if you need to coordinate with others. Another concept that we will now look at to solve these games, which is particularly useful when the games are sequential, is that of backward induction, which is used to find equilibria in repeated games, right? So in these games that I've showed you so far, these are simultaneous games, right? The police interrogation takes place simultaneously in two separate cells, and there's no timing element. However, as I think we can all agree, in many real-world situations, we play a game over and over. Maybe not exactly the same game, but a variation of the game. So this is an important part of game theory because it allows for dynamic effects, such as reputation building, right? Even if you're playing the game anonymously, let's say that we play this game in this class, but I partition you into different groups, and you are somehow segregated by the others, so you cannot see what they're doing on their computers, and I randomize you into different groups, including, the people outside here and the people in the classroom. But even the people in the classroom do not know with whom they have been matched, so they don't know who's playing with whom. Even in such a game, which is not very conducive to reputation building, but if you stick to your role as player one over and over, and you always play the fact, for instance, you will develop a reputation. Player one will develop a reputation, even if people do not know who player one is. So that is important, because this reputation building may be important, especially say that there's a punishment institution, such as peer punishment, and you can also punish other players if they are non-cooperative, for instance. Then player one may be punished a lot. So now I will leave it at that, but I will come back to these repeated gains and show you how backward induction works. Another refinement of equilibria that allows to select among multiple equilibria is that known as trembling hands perfect equilibrium, which is a Nash equilibrium that remains a best response for each player, even when the others have a minuscule chance of trembling, meaning that they may play with a small probability an out of equilibrium strategy. So in the games we have seen so far, everything was deterministic. If you have a dominant strategy, you will play the fact, and that's it. But what if people sometimes, either out of error, they are distracted, they push the wrong button, or out of experimentation, perhaps they're saying, but maybe I should give it a try, I should give cooperation a try. So a trembling hand perfect equilibrium is a refinement that allows for such small perturbations, and if the equilibrium is trembling hand perfect, it still remains an equilibrium, even with these potential shocks. So let's talk more about sequential games, since they are important in real life. These are games with multiple stages, and they're called sequential games. In these games, it is very useful to identify subgames. A subgame of a game is any part of that game which itself constitutes a game. So imagine you have 2 rounds of a game, and you can isolate the decision in each of these. You can consider those subgames as independent games in a way. Start from the last one, that's a backward induction, solve it, and then given that solution to that subgame, you can proceed to the next one. We will see it in practice in a second. The subgame perfect equilibrium is a strategy profile that constitutes a Nash equilibrium in each of the subgames. Subgame perfect equilibria can often be found using backward induction. So let's take this sequential game. So as you see, sequential games can be represented using this extensive form. Unlike the payoff matrices that we saw here, right here, there's no timing. These are useful for this type of simultaneous game, but when the timing is involved, which often involves some kind of bargaining advantage for the first mover, then you say that it's easy and effective to use this kind of extensive form representation. So here you see player one moves first and chooses to go either up or down. By doing down, player one can finish the game, in fact, and get a payoff of 2, and also player 2 will get a payoff of 2. If instead player 1 goes up, then it's a move of player 2. So player 2 actually becomes active only in the second round. In fact, he or she may never play the game, right? Because player 1 has a chance to terminate it already here. But if we get to this node, this part of the tree is the node where you have this new decision on the part of player 2, then player 2 has to decide whether to go left or right. So let's do backward induction and focus on this subgame. You see, you can consider this tree as a separate game, right? Imagine that you got there, never mind what happened before, but for now, let's begin here. So this is where you start. What will player 2 choose given these payoffs? Anyone here or online would like to answer? Yep. Player 2 will choose left, yeah. Why is that? Right, so as you see here, you know, this is the payoff to player 2, and 1 is strictly better than 0. So we have solved this part of the tree. We know that given that we are here, player 2 will do 1. Now we can proceed backwards, and what will player 1 choose? Anyone? Yep. Player 1 will choose up, yes, because player 1 is contemplating, given that player 1 knows for a fact that by playing up, player 2 will play left, hence we will end up here. Player 1 knows that with certainty he will get 5 by playing up, because 5 is strictly preferred to 2, so why would player 1 end the game and move this way? Of course, you know, if you want to be more sophisticated, you may also keep in mind a certain risk element. Even if this is advantageous for both, that they play up and left, respectively, ending up in 5-1, there's a small chance that player 2 acts irrationally, for instance, and goes right, in which case, you know, it would have been safer for player 1 to end the game there. But the payoffs are such that player 1 can reasonably expect player 2 to do the right thing, meaning to go left, and then 5 is definitely better than 2. So this is a simple game, but it has allowed us to introduce dynamics and sequential aspects, and also to show that you know, games need not be symmetric in the sense that here we have this element of first mover advantage with respect to the second mover, who can only choose once he or she is given the possibility to choose at this node. And we found the subgame perfect equilibrium, which, as your colleague said, is up left. Okay, quick recap of what we've been discussing today. We introduced the concept of game, strategy, payoff, Nash equilibrium, where everyone is best responding to the actions of the others, so that assumes full rationality and complete information. And we differentiated between simultaneous games, such as the prisoner's dilemma, and sequential games. We talked about pure coordination games, zero-sum games, where mors tua vita mea, right? I gain if you lose. In order to gain the most, you need to lose the most. Pareto optimality, where no one can be made better off without hurting someone. The concept of cheat talk and its relevance, especially in coordination games. The way to solve sequential games using backward induction, and some refinements such as trembling hand perfect equilibrium and subgame perfection, which means that we are doing the best thing we can do in each of the subgames, in each of those parts of the tree. Okay. If there are no questions from anyone, yeah?
Can you come back to the
question?
What if we have a total uncertainty about the payoffs? Do we just act randomly because we are assuming that player 2 is for certain that he or she will get 5 or 1 or 0, but what if we know nothing?
Yeah. Now that's a good point. In fact, I glazed over it because it complicates matters, but game theory can accommodate uncertainty. Now there's different levels, I guess, of uncertainty. You could
because if we have kind of uncertainty, not so deep, you can use probabilities.
Yeah. Exactly. So before, when I mentioned somewhat loosely the fact that player one is taking a risk in a way by letting player two decide, I didn't mean it in a probabilistic sense, right? Because in this game, everything is certain. So the payoffs are certain, right? There's no uncertainty about it. But you can also do games where, for instance, there's asymmetric information. That's one kind of uncertainty. So for instance, player two may observe the outcomes of his or her actions, but player one may not observe this. So in this case, you do like a dash line to represent this kind of asymmetry, to say that from player one's perspective, she doesn't know exactly what goes on there. So that's one way to accommodate it. And if you have a well-behaved problem, meaning that you can attach probabilities, then you can still compute your best outcome. Let's say that there's 50% chance that you end up in either branch. You could do expected payoff and still, with the concept of sub-imperfection and backward induction, try to do your best course of action. Of course, it depends on the level of asymmetric information and the level. It may be such uncertainty that we actually have ambiguity over the distributions, as we saw before. In that case, it becomes difficult to use this framework. So this framework requires that we can attach probabilities. Related to this topic, there's also situations in which, even if the payoffs are certain, you are indifferent. In that case, the equilibrium concept is a bit weaker in the sense that you're indifferent, so you generally randomize. So you do one strategy with 50% chance and the other with 50% chance as well, because you are indifferent. Of course, these equilibria are less interesting in a way because they're less stable, right? Because a little departure from that, and you have a strict preference for one of the two outcomes. But for the purpose of this brief introduction to game theory and behavioral game theory, we will assume almost always that the payoffs are known and that they are certain. There's no probability weighting. Any other comments or questions? Okay, so let's talk about behavioral game theory, since we can marry the two, right? We've talked about behavioral biases and fallacies. We've talked about strategic interactions and how to capture them with game theory. So let's try to bring the two together. So one important game that has been used in experimental economics to get into the black box of our decision making and also ethical considerations is known as the ultimatum game. In it, again, this is not a simultaneous game, but it is a sequential game. Player one has a fixed amount of money. Say you're endowed with 10 euros, and you must choose which fraction of these 10 euros to give to player two, the second mover. Again, you could decide any value between 0 and the very generous offer of the entire sum to player two. Player two then moves. Of course, if you decide as player one to give 0, the game ends. It's a bit like before, right? But if any positive amount is chosen, counter to standard rational calculus, player two then does have the chance to either accept, in which case the money is split the way that proposer player one suggested, but player two could also reject. In that case, both go home with 0. So it is not that dissimilar from player two here choosing right, which led to both of them getting 0. So they have played this game with people in different societies, different education level, different democracy level, different development level, wealth, even in tribal communities. And well, there's variation, but empirically responders tend to reject offers by the proposer that are below €2 or 20%, let's say, of the pot. But such low offers would be rare. So anyways, it's hardly the case that player 2 rejects, because it's hardly the case that offers below 2 are made. Generally, offers fall in the 30 to 50% range and typically are accepted. So that's interesting, because what would the rational prediction be from the point of view of player 1? If you act selfishly and according to standard rationality reasoning. Yeah.
You would offer 1 cent.
Yeah, exactly. You would offer 1 cent or even 0. I mean, it doesn't really matter, but yeah, any positive minuscule offer will be accepted. And so, you know, and even if you get to player 2's level, let's say that I'm player 1 and I offer you €1 out of 10. If player 2 is rational, she should accept still, because €1 is better than going home empty-handed. Yeah.
Maybe it's also dependent on the starting point of the 2 players, because if I am player 2 and you offer me €1, and let's think that I already have €1 million, I need more euros to achieve the same level of marginal utility. So maybe I would like to receive like 9 euros, otherwise I don't care about it.
Yeah, I see your point. So you're saying it's such a small offer that it makes it irrelevant. But this finding is, here the example is €10, but the finding is quite robust to different stakes. Now, of course, stakes need to be adjusted to your relative wealth. So the most common population of subjects, as I said last time, is students, and generally you're in the range of 10, €20 split. So you might say, okay, I'm not going to be rich, but €20, you start taking it seriously, no? But they have done it using different stakes, bigger stakes, and also they have gone to tribal societies and give the equivalent of up to a month of wage. So this is one of the most replicated experiments ever done, and with people from all over the world. And again, there's variation, but it's generally the case that player 1s offer something in the range of 30 to 50%, and it generally gets accepted. Of course, you may find there's always a small minority of people. But insofar as you believe that the stakes are sufficiently high, that even if you're wealthy, you care about it, then people will do what they think is best, or they will think seriously about it. So I think in terms of external validity, this is not a particular cause of concern for this game. But there's good reasons why these offers are made, if you go beyond the standard model, of course. So let's visualize this ultimatum game in a form that captures the sequential decision making. You see there's, let's, for simplicity, assume that the offers can only be in discrete levels, increments of €1. So you can either offer €0 as a player 1 all the way up to 10, here switch to dollars. And for instance, if you take this branch here, player 1 offers 40% to player 2 and 60% to self. And again, player 2 has the option to either accept, in which case 1 goes home with $6 and 2 goes home with $4, or reject and both go home with 0. This is how you visualize. And again, rationality would basically lead us here, and player 2, even with the 0 offer, would be indifferent and possibly accept, or even, okay, if you want to be on the safe side, you would offer 1, and player 2 should definitely accept under rationality. But that's not the case. Consistently across the world, people that are confronted with 10 or 20% of the pot, they find it probably unacceptable. So we are entering into, even if it's such a simple game, it already captures some notions probably of justice and fairness and ethical considerations. Strictly speaking, a game is defined in terms of utilities, not in terms of dollars. So for simplicity, let's just assume that your utility of $5 is 5, and so on. So x, utility of x equals to x, linear utility. If so, the only subgame perfect equilibrium is the one in which player 2 accepts all offers and player 1 offers nothing. Notice that because it's a sequential game and it is can be decomposed in two subgames, for it to be a subgame perfect equilibrium, which is the extension of the Nash equilibrium to sequential games, you have two decisions, right? That of player 1 and that of player 2. Even if you never get to the second node, you need to specify the entire course of action, so it would be acceptance for player 2 and 0 offer for player 1. That's the Nash equilibrium, the subgame perfect equilibrium. Now let's take an even more extreme game, very similar, but here you remove, in fact, the choice. You still have a player 2 that is affected by player 1, but player 2 here has even less bargaining power, in fact has 0 bargaining power, can only witness the decision of player 1. Now, again, if you're rational and you're player 1, why would you offer anything? Because this player 2 is completely unable to either accept or reject, has to accept. So it's an ultimatum game where player 2 does not have the rejection opportunity. Here we find that offers are a bit below. Remember before it was 30 to 50%. Now they're about 10 to 30%, but that's still sizable, definitely strictly greater than 0. So if you assume that you're self-interested, your utility only depends on your own payoff X, this is not consistent with the subgame perfect equilibrium, right? The only subgame perfect equilibrium is where the dictator offers nothing. In order to rationalize the observed empirical frequency of donations that are above 0 and are in the neighborhood of 20–30%, you need to somehow make the model a bit more realistic and more general and move away from this fixation with X only, your own payoff. And you can do that by introducing social preferences that reflect other people's attainment. So assuming there's only 2 players, player 1 gets X and player 2 gets Y, you need to put both of them in your utility function. So if John derives positive utility from Mary's attainment, then John is said to have altruistic preferences. You attach positive weight on the payoff of the other player. But it could also be a type of spiteful preference or envious preference when John actually derives negative utility from Mark's attainment, right? So let's say that you're jealous about or envious about the higher wage that your colleague is earning. In this case, you have your social preferences display envy. We can have other kind of non-selfish preferences. For instance, Rawlsian preferences or preferences for fairness try to maximize the minimum utility associated with the allocation. So in a way here you care about avoiding the worst scenario, right? So you want to be sure that even if things play out badly, they're not too bad, kind of a precautionary principle. A person who wishes to minimize the difference between best and worst off is said to have inequality-averse preferences. This was introduced by Fair and Schmidt in 1999 with a very simple yet powerful way to capture this dynamics where your utility function not only depends on your own payoff, but also you have a term that is generally weighted below 1, right? Otherwise, you care more about this difference than about your own payoff. So the assumption that the main driver is your own x remains, but you have x plus alpha times what they call advantageous inequality aversion. So the part that you suffer a penalty from being better off than others, than the other, and also a part with the parameter beta multiplied by the opposite, meaning when you're the one who's worse off, and that you suffer this utility from being worse off than the other. So this can accommodate both spiteful, envious preferences and altruistic ones. Individuals who want to maximize the total amount of utility have a utilitarian preference, right? So this is, in a way, the stance that is generally believed to be taken by a benevolent dictator or a social planner who's maximizing collective utility of the society, which would be the aggregation of the individual utility. So this may sound a little bit abstract, so let's try to put it in our simple utility framework. So if you have egoist preferences, then your u, which in principle accommodates also y, actually is again only a function of x. Here we have square root of x, so it's a non-linear, unlike before, utility function with some concavity, but again only x as an argument. Utilitarians will instead have this sum of the, remember they care about the minimum for both, so square root of x plus square root of y. If you display envy, then you deduct the utility, the payoff of the other person from yours. And if you care about the least well-off, you try to maximize u of x and y, where the arguments are both x and y, but using the minimum function, right? You're focusing on the least well-off. Any questions? Okay. So, in a way, these simple games make it clear that just taking, not only focusing on x only is not very realistic, but also that we as humans, and actually animals do this as well, care also about reciprocity and even intentions. What they can extrapolate, they can infer from the choices of, say, the other player, player one, given that you are in this part of the tree, given that a certain action was taken. So in a way, in your utility function, you also attach value to whether the other player had an option to do something more altruistic or not. So whether a responder will accept depends not just on the allocation, so 80-20, 30-70, but also on what the alternative available to player one was. And you can distill it into a simple framework in using experiments as well. This suggests that responders base their decisions in part also on what they perceive. They may be wrong, but what they perceive the intentions of the proposer were. If that is the case, and it is an empirically robust finding, respondents exhibit positive reciprocity when they reward others with good intentions. So if they think that player one did something out of good intentions, they're more likely to accept, in this case, or reciprocate by further doing a nice gesture to the proposer or the first mover. The opposite may take place under negative reciprocity, in which case you tend to punish players if you think that they had bad intentions. So let's try to disentangle some of these dynamics using the trust game, which is played by a sender and the receiver. So it is again a sequential game where you have the sender moving first and the receiver moving second. Sender transfers some amount to the receiver. So imagine again, you're given 10 euros, you're player one, you're the sender. You can keep it for yourself, or you can send a fraction or even all of it to the receiver. Now, unlike in the previous game that stopped at the second iteration, either acceptance or rejection, here there's an interesting twist. First of all, the game can continue, and also there's some kind of social bonus in this act of trust. So the idea that it is convenient and efficient for everyone to do this transfer, because so long as they trust that it will be reciprocated, because there's money to be made. Like when you transfer, unlike before, it was just splitting the pie, right? I keep 50 for me, I give 50 to you. Now, the idea that if I give 50 to you, that 50 becomes bigger, the pie expands. So a typical multiplication factor to introduce this social element, you know, that you are somehow doing something that benefits society, is to multiply it by, I don't know, a factor of 2 or 3, right? So if I give 5 euros I transfer 5 euros to the second mover, the receiver the receiver receives, say, 15 instead of 5. And then the receiver has the opportunity to transfer back money to the sender, to reciprocate. So you can look at positive reciprocity in this framework. Any guess about what the subgame perfect equilibrium, if you have selfish preferences, u of x equal to x is? It's not a trick question, it's an easy one. Feel free to intervene from Teams as well. Otherwise, I will suspect that you're all sleeping on your couch, which is probably true. So surprise me. Anyone? Okay, how about here? Are you sleeping as well?
Maybe everything, the maximum you can send.
If you are rational and selfish and you only care about your own money?
No, okay, I was wrong.
Okay, so it's the opposite, right? If you are selfish, you will just keep the 10 euros to yourself because you don't trust that the other person will reciprocate. You only care about your ex, and you keep it. Because not only you care about your ex, but you assume that the other person has the same preferences. So you assume as player 1 that player 2 has utility of the form u of y equals to y. Now, if you do that assumption, you know, then you know that if you're transferring 10, which gets multiplied by 3, so player 2, the receiver, receives 30 euros, but you also think, you know, this player will just keep it, and I will end up empty-handed. So that's why the prediction under these preferences is 0, which is a waste of money, right? Because this money gets multiplied, and if there's trust and the receiver were to give back, both could go home with more money. So I've already introduced, in a way, this tension between the social good or some kind of benefit from cooperation, and that is captured even more directly by the public goods game, which is an n-player version of the prisoner's dilemma. So let's start with a very simple 3-player version to keep it as small as possible, but bigger than the prisoner's dilemma. So suppose there's only 3 of you, and you have to play this game together. Each of you is given 10 euros, and each can choose to transfer that money to a public account where it will be multiplied this time by a factor of 2 and redistributed evenly among all players, right? So each of us has 10 euros. If we keep it to ourselves, there's no social reward. If we put it in the public pot, let's say that we're all of the cooperative kind and we have preferences that allow for this, what happens? We put each 10, right? So there's 30 on the public pot, it gets multiplied by 2 thanks to the public good reward. Say, you know, you're building a bridge, you're doing something for the community, you're mitigating climate change, there's gains to be made or losses to be avoided. And then you have 60 euros collectively which gets split equally among all three. So in this scenario, you all go home with 20 euros, which is better than 10. Now, if you have utility U of x equals x, what is the Nash equilibrium and what is the Pareto optimal outcome? Anyone?
We have new writing, so I don't give money and I still get something after that. Everyone has already some money.
So the Nash equilibrium would be defect, defect, defect for each of the three players, right? Yeah. What is the Pareto optimal outcome? Cooperate, 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 because for the entire society would be better off. Each would go home with 20 instead of 10 euros in this scenario. Now, there's another game known as the beauty contest game, which is slightly more complex to anticipate the outcome of. So imagine that you have n players picking a number between 0 and 100 inclusive, so it could be 0, could be 100 as well, or any number in between. The player closest to some fraction, arbitrary, let's say it is 2/3 of the average, wins. Does it make sense? So you have to, you win if you pick the number that is closest to 2/3, the closest to that chosen by 2/3. Can you guess what the Nash equilibrium is? It's a little bit tricky and it requires a little bit of thinking about what the others do, and so maybe
I'm sorry, are the players aware about the selected fraction?
About?
The selected fraction, do they know that they have to go closer to over 3?
Yes. It is common knowledge. Yeah. So this is a tricky game because there's no strictly dominant strategy, unlike in the games we have seen so far, where, for instance, in the prisoner's dilemma, the dominant strategy is always to defect. But there is a unique pure strategy Nash equilibrium nevertheless. And in order to do that, that is helpful in introducing another way to solve these problems. And this is known as iterated elimination of weakly dominated strategies. It's a very lengthy way to say it, but if we look at it in practice, it may be easier to appreciate what it means to do this iterated elimination of weakly dominated strategies. So guessing any number lying above 2/3, meaning 66.6, is weakly dominated for every player, since it cannot possibly be 2/3 of the average of any guess, right? Because you're picking the number that is already 2/3. So you can remove all the guesses that are weakly greater than 2/3. But once you remove those, remember you have to guess what the average is. The strategies are eliminated. Once the strategies are removed, any guess above this time is 44 and 4/9 is weakly dominated for every player, since no player will guess more than 2/3. And 2/3 of 2/3 is 44 and 49. So at the second step of this thinking, you can remove also any offer, any guess above 44 and 49. You can continue like that until you get to 0, basically. So the winning guess will be 0 after you do this iterated elimination of dominating strategies. Okay, so we have talked about quite a fair amount of games and their implications for the rational model and also for social preference models. Specifically, we have talked about the ultimatum game, where player 2 can reject, the dictator game, where player 2 does not have the option to reject, trust game where money can be made if we trust one another. Public goods game that also involves some level of trust, but in a different way. Here we need to assume that others will cooperate in order to also cooperate. So there's the similar aspect that if I'm the only sucker who defects, that I will be free-ridden upon, and that will be bad for me. But if I trust that others will cooperate, then I may be able to escape from the Nash equilibrium. And then we briefly talked about the beauty contest game. In terms of preferences, we have seen both altruistic, envious, Rawlsian, that try to avoid the worst outcome, inequality averse, and utilitarian preferences. And finally, the aspect of positive and negative reciprocity. I think it's a good time for a break. Let's come back at 2:05 in 15 minutes. Unless there's a question.